Okay, good morning, everyone. I hope you can hear me. Please, someone confirm. Yeah, okay, okay, that's great. Okay, we can still wait a bit for the rest to come. So just for the beginning, I sent you the information about the selection of topics. As I said, about 1/3 of the lecture are the topic that can be optional, depending of what are your special interest. I've seen that some of you already has selected. So here you have the link in the portal and just choose of what would you like to hear about. I see that the vision and ROS are currently the winning subjects, but I say about 4 or 5 we will uh, we can tell about from depending on your choices. Okay, another thing that has appeared, so under today's lecture, there are 3 papers about the Remedy robot. We will talk about it today during the lecture, so if someone is interested a little bit more, you can also reach it here. Okay, and let me pass to the subjects for today. So the subject I would like to tell you about is a bit general, but I hope it will be useful for preparing the project that you have and working on the project, because it will be generally about the design of the robotic systems and the design approaches that are used to make this project successful. So we'll start with general design phases. Then we will show an example that was done here at university, at least partially, and we'll say also about the control architectures. So as you might know, because that's the general approach to the design process, you can find some graphics of that type in any books of the engineering design, and that generally says, okay, division to the phases can be different, as we will show in a while, but what is important and what you need to remember is that it's not a linear process that starts somewhere and ends at certain point, but in general, it is a wheel. So we have multiple iterations. We go from the beginning, define the problem. That's more or less the starting point where we enter the wheel. We start with the definition of the problem. We go through some phases, develop a proposition of the design, make it, evaluate, and then we find in this design some new problems that needs to be solved, and the process begins with the next iteration. As I said, okay, depending on the authors, this process can be divided or named. The elements can be named in different ways. So you can find from another book, a cognitive process approach. But you can see that again, it has certain elements that are in common. So firstly, you have the analysis. So you think of what really your problem is, and then how to solve it. Then you make when you already know the method, how you want to solve the problem, you have a design when you prepare your solution. After the design, you have the building or constructing your solution in any form. Then you have the tests, and then you come to the analyze again. So you compare your result with what you wanted to achieve, and usually you make the next step and start from the beginning. That may be not visible to everyone, but when you analyze what happens with different products, you will see that they can change. There are small changes in the design that are always some improvements for the things to be better, to work better, or if not, then to be less expensive in production, or with improving any other factors in the process. What that means? Okay, so that's yet another approach. As you can see, naming is different, but generally it's always the same way. What it usually means that you have some that what you have in common is that the phases that you should also include in your projects. So we already started in the planning, that is kind of the analysis of the problem and analysis of how to solve it. Soon you will need to propose the solution, prepare the solution, and analyze the results that you obtained. Of course, we will probably not have enough time to make full wheels, full turns with another approach to the whole project, but probably we'll have these small loops inside certain projects when, for example, you write a first version of your software, then you decide that you want to improve it and correct it, and then you will have another iteration. Okay, so how these steps can be divided in the certain task that you need to achieve. So in problem definition, you firstly need to determine what is really the problem and what objectives you are going to reach. In fact, that's something that those of you who already submitted the charter, you have already passed this part. Then imagine various use cases. That's usually partially done. In a project, I didn't expect that you write it, but it's good to have certain ideas of how your solution will be used and what will be important for the user. We'll also say a little bit later about the user-centered design. That is kind of the approach that is kind of standard for the modern design. So that should be something at the beginning. So you don't think of how to solve an abstract problem that you are thinking about, but the product, the design that you are preparing, someone is going to use. So you should think of what the user of the project, maybe you will be the user, but what would you like to have and how to operate the design that you get at the end. And again, those are the parts that you probably already have in your charter. So defining the objectives, that was certain. We also said about the selecting the required objectives and some supplementary. In bigger projects, you can just put them in order. What is more important, what is less important. In fact, if any of you will work with or already works in software development, now the so-called agile methods of software development, they usually also use this approach at the project planning level. When they say you have the backlog, so all the ideas that you want include in your project somewhere in the future, and then you select what is currently the most important part to do in the next sprint, so in the next period of work. Of course, there are some parameters of the solutions. So especially in engineering, you want to have some benchmarks. Okay, if you make a robot to do certain tasks, you probably have some dimensions, payload, velocities, whatever parameters you are important for you, and they also can be defined as some measurement, the values to measure the quality of your final solution. Then the constraints that we already talked about on the project, and it's good to have everything written. That's why you were writing the charters, just not to forget of what you really wanted to achieve. It is not a big risk if you are just doing the project in short period of time and in small groups. But if the group is bigger and the time for whole project is longer, and there can be project that last for many years, then it is good to have it written of what were the results of the plan. And one thing that's also worth to remember, that usually these documents are not fixed at the beginning. They usually are being changed and updated according to the needs and according to the results of you obtain on the way. Okay, so when you already know what to do, that the second part is the research and brainstorm. And here I have limited it to mostly to the robot, so it's a little bit less general. So if you already have the objectives of what the robot should do, then you may think of how to transform it to the robot design. What does it mean? So, for example, you may imagine that that your objective is that you want the robot to carry, for example, mail from one office to another. Okay, so that's the idea of what the robot does for the user. So the user wants to call the robot, give it a mail to delivery, say where it is supposed to be delivered, and the robot must to deliver it to that location. But that's the perspective of the user. Now, in this research and brainstorm, you have the perspective of the robot design. So now you can say, okay, so what we need in the robot. So the robot needs to have a function to be called by the user. So maybe some interface with the wireless network to receive the call to arrive to someone sending the mail. Then it needs to some mechanism to receive the mail. Maybe a gripper to grasp it, or a box to put it in. Then another function is, of course, if it needs to go, it needs to have some mobility function. So it needs to move. If it needs to move between offices, then it probably needs to detect people and avoid people, and so on. So those are the simple functions of the robot that it must have to fulfill the objectives that you planned in the project. Then again, a core element of the design. So you may think of, okay, maybe some elements are already fixed. For example, if you want the robot to move, so you need some movement mechanism. You probably need some wheels and some mobile platform for it. But for example, receiving this mail can be done either with the manipulator and the gripper, or maybe you can say, okay, we just open a box and the user itself puts the mail in this box. So some elements are core elements that must be. Some elements are can be solved in different way, and so you can identify them as alternative design solutions, and then you analyze it. And finally, you want to get a design the structure of the project, of what you what are those elements, how they are connected with each one together. Okay, how these goals are achieved. You have the steps here. So usually, firstly, you need to get somehow the information of what you really need. If you are not a user of the system, you usually need to ask other users of how to do that. What are their needs, in fact. Maybe present the alternative design and say and ask what will be preferred. Of course, to present these alternative designs, you need to know what are the possibilities of what you can do, what is worth to do, and if you have this alternative, you just discuss of what are the advantages and disadvantages of each of the options that can be selected. So maybe something is easier, something is cheaper, something is more complex and less reliable, for example. So all these factors can be influencing your decision of what you finally do. Okay. So what now? Now the time for prototype, and yeah, those are some questions to you, and maybe you already can answer of what do you think of what is prototype? Why do we do prototypes? Is one prototype enough? And how to prototype? What would you say? Why do we make a prototype? Anyone would like to say something?
To test the design. Yes.
I couldn't hear the beginning. Could you repeat?
To test the design.
Yeah, we are going to test the design. So maybe the other. Do we expect the one prototype, or does it need to be the design of everything or the complete system?
No, just the basics.
Yeah, we can just have the basic. For example, we can have a critical component that we are not sure if it will work or not. So, for example, with this example with the mail delivering robot, we can say, okay, we already know how to move with a robot between the rooms, but we don't know how to collect the mail. So we can just make a part that is collecting the mail, put it on a fixed base and say, okay, let's test if it will work with the users. We can then present it to a user. We can say, okay, what are they, do they like it or not? And that's we can test. So we can test if a part, especially the part that we are not sure if it will work, if it's a good idea or not. And usually the difference between the prototype and the final version is that it misses some features of the final design because it's still the testing phase. We still can get the answer that there is something wrong and we need to change. So everything what is not necessary for the certain test will not appear in the prototype. Okay, so the question how to prototype. So there are different methods, and currently the main approach in almost all fields of engineering is using the simulation models. Why? That's quite simple, because making a model in a software, it's much easier and much simpler than making a physical model. So especially when we say about the mechanics and the physical elements. So machining of components or assembling a bigger construction out of single components is kind of expensive, both in the sense of money and in the sense of time that needs to be spent. And the simulations on the computer make it much easier. So especially when we say about redesigning and checking alternatives, it's much easier to modify certain elements like dimensions of the robots, some ways it operates, even replacing whole parts of the robot with another one. It can be much easier done in simulations than in a physical system. But what about the disadvantages? What will not work in simulations? How do you think? Okay, usually the simulations miss certain physical features. So although recently the simulation of physics is much better with each year, in fact, but it still is not so realistic as it could be, or it's still, the simulations includes only these elements that you design, and it does not include all the additional things that may happen in the real world. So you can, for example, prepare a simulator and some scene for the robot with vision. You can put some artificial light, but the light will be exactly in the way as you plan it. And if you didn't include the changing sun position and changing sun color in sunlight coming into the room, you will not have it in simulation. So the simulations usually has only the elements that you put in there to simulate, and the real world is not that simple. Moreover, in some systems, for example, like when you take the RoboGuide from Fanuc, you can design the movement of the robot, and what happens inside the robot is realistic. It happens exactly what is in the controller, but the external world doesn't have physics, so especially it doesn't have the gravity. So if in a RoboGuide you put a box somewhere in the air, it will be left that and floating somewhere. What of course will not happen in the real world. So some things cannot be simulated or are not simulated with the software you have, and not every aspects of your design you will be able to test in simulations. So usually after the simulation phase, you still need to make a physical prototype. But because of the cost and the time, one tries to use the computer simulations as long as it is possible. And when we present it in some graphics way, we can reach something what is called the model-driven engineering. So when you start somewhere at the top with your idea and the model, then you the meta model. So it's at this functional level. So you don't know what are really the parts of the system, but what is the general way how it works. That's the most abstract. And here you have also the widest design space, so widest possible solutions. And then you make it more and more precise. So then you define an exact model of what is going on. Then you divide the model into the components. Then the components, you make the code. What happens inside each component, and then you get this real robot. So we go from the abstract level to the concrete, but of course, this abstract meta model is not something that you can use. But when you start to go deeper, you can make some tests already. So for example, at the components level, you can check if the inputs and outputs are correct. If you say, okay, let's imagine that we have a data of the certain type, we can test if the data transfer is correct. Of course, we will not know yet whether the data itself is correct, but the flow of the data we can already test between components, and so on. And then getting to the code and the most usable way. And of course, the design space is, we get to the narrowest part when we have only the design that we really did. As we said, what we have is at the beginning is the idea. Somewhere in the middle, we have partially a simulation and partially the physical system, and finally we have the runtime thing. Okay, and then okay, we already said why we use the simulations. We said about reduced cost, reduced time, improved quality. That may be not clear in the beginning, but in fact, it is the results of the time and cost, because usually in every project you have the limit of time and cost. So if you can spend more time on the project, or you can include more iterations in that in the same time, that's why you get this improved quality. Easier to evaluate. Again, you can prepare multiple tests. I've sent some of you the GTC link to GTC conference, and one of the idea that NVIDIA has, and that was also in one of the projects that you could select with this Omniverse simulation software. It was one of the example of why that it is visible that simulations are easier to evaluate. So what was the idea there? The idea there was that deep learning algorithms or neural networks algorithms require multiple examples, multiple situations to use for teaching of the algorithm. And for example, in certain applications like autonomous cars, you will not be able to provide that many situations, different situations, with the real car and recording of the things that happen on the road. Moreover, some situations you will be not able to provide because they mean the situations that may lead to a crash, and you don't want to crash with your test car, but the training data should also include such situations. So what was the idea of the NVIDIA? To create the simulator that will be as realistic as possible, so they can create multiple training data, especially for autonomous cars, and not only to create it by hand, but also to be able to create it automatically using certain algorithms with randomization. So you can really create the amount of the data that wouldn't be possible to provide it from the real world or from the human prepared data. Okay. What else we get when we go from using simulations? So firstly, when we have complex systems, and usually the robots are complex systems, we can check the interaction between the systems yet at the simulation level. And well-designed environments for such tests allow both working only with simulations, but also mixing real-world components with simulated components. So we may have only part of the robot working, and the second part being virtual, and we can still test if they connect well, if the especially the data flow works correctly between them. What else? You can do the parameter tuning, and then you can check behavior of the system in different conditions. Maybe you don't want to do it in the real system, not to damage it or to destroy it. And and that parallel development. So if you have, for example, simulated hardware, you don't need the hardware components to start developing software, and you can already start writing a code for the hardware that is yet to be built, and that it will still work. Okay, so those are the advantages, and the terms that you can sometimes meet when you hear about it. It's so-called rapid prototyping, or the virtual environment, and reducing time to market. So those are the terms that you should be aware of, that they can be used in that context. So when you say about the model-based design, we can and the graphics that we had a few slides before, we can say that we can mix the simulation with the hardware, and we can mix it on different levels. And again, there are some terms that you should know what they mean, and also the abbreviations, because they can appear quite often. Uh, and it's good to know what people talk about, or maybe even write about in the recruitment process, for example. The most general part is model in the loop, when we only have the simulator. So both the real objects and the controller are only the virtual beings. So you don't have the real system. Uh, uh, you don't have a physical system. You don't need to work in real time because the simulation time may be different. Then, and what may happen, what you also do not need to have it on the same processor that is your destination processor. So, for example, the modeling the controllers that you did in MATLAB is the example of this approach. So we use the Simulink, we put the model of the robot, we put the controller around it, or model of a process and controller around it, and we see what happens. That's the model in the loop approach. Then the next step in the model-based design is the software in the loop, when still everything is on the computer, but the code of the controller that you write is already on your target controller. So it's not the code for the general processor, but if you write for the microcontroller, it is the code written for that exact microcontroller. So it uses the resources at the level of this microcontroller. It uses the instructions that are available for the microcontroller, and also some specific features that may happen and may not be. They may be limited comparing to your general simulation software. That's why it gets a little bit more realistic. It doesn't need to be real time, but it is preferred that it works also in the real time. So the time steps or the frequency of the clock for the microcontroller is the one that will be on the destination system. Then next step is the processor in the loop, when you don't not only use the code for the microcontroller, but also use the microcontroller itself. So you have your object simulated, for example, in a MATLAB, but the controller connections to the controller, the interface goes outside to the real microcontroller board, and the commands from the microcontroller goes back to the simulator, and the model of the object is virtual, simulated on the computer. Then the computer must be real-time computer, but the controller is working on the target platform, on the one that will be deployed finally. Those are the changes on the on the side of the controller, but you can also have the hardware in the loop, which is similar to the processor in the loop, but also using the real input and output devices. So either here the model was still completely virtual. In the hardware in the loop, you use the input and outputs of the physical microcontroller. You don't connect them, for example, by USB or some other network. You use the real physical I/O devices, and that it comes even more realistic. And finally, we get the target system validations, when you already use only the physical systems of your target. So target objects and the target controller. So as you can see, the virtual environment can be used on the different level from either completely or in different parts. And of course, you not always need to pass all the steps like here. Sometimes you just go like, okay, we start with the model, we test the model, prepare the software that works, and then we directly go to implement it on the destination hardware. Or we just do the mill part and mill, and we don't need to pass all the steps on the way, but it's good to know that such possibilities exist. It's good to know what people mean if they use these terms. And it's good to know that there are such possibilities. And as we said, the more you spend on the higher levels with preparing and testing, the less time and less cost you spend on the preparing the final system. You may test it better, and you may improve it at the lower cost than going directly to the physical system. So that's worth to remember. Okay, so those were some drawings, just explaining what we had on the previous slides. Okay, so we already said about the idea and concept, components and integration. So what about the verifications? When we want to test, okay, when we already prepare the design completely, we want to test it. But of course, as you can imagine, whenever you test it earlier, you can avoid more errors. And if you the later you detect the error in your project, then the cost of removing it and the time that you need to spend on improving the project will be longer. So what happened? For a long time, the approach for the system was building the whole system together and testing everything together as well. And it's appeared that it's not really the best approach. Somewhere around 2010, 2010, yes, there was a BRICS project, that was the European project, to see how the robots are developed and to work out certain design approaches that will be successful. And in these two papers that appeared in a journal by Brugali, the component-based robotic engineering, these papers presented the analysis of the robotic projects that were already finished, and what they compared the different design approaches, and the results were that the so-called component-based design is the best approach in the sense of the highest probability of the success and the lowest delays in the delivery of the project. What is the component-based design? In fact, it was nothing new in general, because it was already known in software engineering. In software engineering, it was really old. And that was, in fact, implemented in the Objective-C And for the next computer, I'm not sure how many of you knows the history, but the next computer was the idea of Steve Jobs before he moved to Apple, and before the Apple success. So this was the similar idea that he had for the Apple, but at that time when he presented it, it was just too complex and too expensive to be successful. And also the Objective-C was a language that appeared between the C and C++. It was like a first attempt to make the C objective, and later on it was improved in the form of C++. So generally, what was the idea? That instead of developing the whole system together, you just try to split it to the small components. And these components in the software, they were simply objects. The objects, as they were defined in the object-oriented programming, they should have some own properties, the operations that work on these objects, and the interface that provides some functions and the values that are available from outside, but they are limited. So only a part of the things that happen inside the objects are available outside. Also, the objects should have a certain defined functionalities, what they and responsibilities, how that's called in software engineering. So they should be somehow closed entities to work with. Okay, the idea was already well established, but it didn't work in robotics at the beginning, mostly because the devices were changing a lot. So there were new sensors, new components, new motors, new controllers, each of them working in a completely different way. So the one of the advantages of the object-oriented software, that is reusability of the code, was not really working. Another limitation was that the companies work separately, and they were hiding their solutions in the proprietary software with quite strong limitations to and copyrights that didn't allow anyone else to use it. So that was the reasons why in early robotics it didn't work. But then it started gaining popularity. That, as I mentioned, the BRICS project showed that the component-based design gives the higher success ratio of the projects. It was also included in the recommendations that are called the best practice in robotics. It's also in these papers quoted here. But of course, that was a part of the theory, but also came the practice. And the practice was they appeared the frameworks in which you naturally worked with the component-based design. At the beginning, there were some other frameworks that we can skip here as they are more historical, but currently most of the places use ROS, and ROS is in fact very strongly representing this component-based design. We'll talk about the ROS later, probably, as you vote for this in your lecture topic request. But we can just mention that the basic element of the ROS is the so-called ROS node, which is a piece of software that has a certain function and defined interfaces. And in fact, the kind of this ROS node is the representation of this component. They can be, we can say that they are exactly the same. Okay, so what is this component-based design and how it is how it is defined? So firstly, the component is complete. So it's a unit of the deployment. So you just put the component and you don't need anything anything else to make it working. It has some maybe it has some configuration. You need to configure it, but the component should work and be usable itself in the range of its input and output. Then it should have well-defined interface. So you don't need to look inside the code of what's going on, because everything what is available for you, it's available through the interfaces. And what else is that the functions that are defined by the components should be general, so it should give some reusability of the of this component. What does it mean? For example, a component that the components, ROS nodes, to operate, for example, LiDARs, all of these components have the same interface, and the format of the message received from any type of the LiDAR is standardized. So when you want to connect to your software a different LiDAR, you change the ROS node from the LiDAR that you had, for example, from SIG to the LiDAR that you have from Hokuyo, but the type of the message you receive is exactly the same. So you don't need to change anything in the other part of the software, because the message, the interface is exactly the same. And what else we have here? Okay, it is black box. So in fact, it's related with the interface. So what is inside the box should be not interesting to you. If you have, for example, a mapping component with certain inputs and outputs, you don't need to be to know how exactly this mapping component works. It just, you know, that it gives the map for the robot. It is important because then you can replace this component with another component that has the same function. It gives you also a map. It can done it in a completely different way, using a completely different algorithm, but if it has the same input and output and the same functions, then they can be replaceable. So you can replace the component with another one without changing anything else in the system. And because of this, these two features, you can imagine why the development of such systems is more rapid. You write the code once and you can use it in many systems. And again, when you want to change something, you don't need to change everything. You just take out a block with one component, replace it with the same block of another component, and they should fit together, and the system will work, will still work. So that's what we are going to achieve, and that what happens in this type of the system. Okay. So the advantages we already talked about. So what special design techniques this component-based approach provides? So firstly, the parallelization. So if the components are separated and defined only by inputs and outputs, you can develop them in parallel because each of the developers knows what the inputs it receives, what output it should give, and doesn't have interdependence with other components a part of it. So the development is independent. Then you can have the templating. As you said, okay, you can have a template for any LiDAR. You know what you need to give into the output. You just look at the documentations of the certain hardware, and you need probably to communicate with this hardware in a different way. But what happens inside and what you send to the outside world will be probably solved in the same way. You will probably have the same functions to transform it, for example, in between different coordinate systems, from the LiDAR that usually works in planar coordinates to, for example, Cartesian coordinates. But a part of having different communication channels, as you can have one LiDAR with serial port, another LiDAR connected with Ethernet. But what happens in the software may be in big parts the same. So you can use certain templates, templates of the code. The same, you can use certain templates of whole components. When we will talk about the ROS navigation, you will see that big navigation blocks contains some components like global planner, local planner, mapping that have certain connections between them, but you can replace a local planner with another local planner and still whole navigation will work. So we have also template of connecting multiple components together. What else? Something related with the parallelization as well. So when you have some components that are not ready, you can replace them with mockups or dummies. So some empty blocks, they do not have a proper functions ready yet, but they can produce some data, maybe generated from the simulator, maybe just constant data or random data that can still populate the system with some messages arriving that you can test another parts of the connections and another parts of the systems, even if some of the components are not yet ready. And what we said about this iterative improvement and replacement, as the components can be easily replaced, you can then build your system more quickly, as you can put the system from the blocks that are already prepared, maybe even designed and implemented by someone else, check that it's working, and just when your own blocks are ready, just put them, replace the first versions with the next ones. Okay, and that's the example how it works in a general robotic system. So we can usually have this high level, okay, the applications components, the components that connect the robot to the user. We can have some middle components that do certain robotic specialized functions like kinematics or path planning or navigation. And then we have the low-level components that can be either device drivers, certain calculations libraries, but also some simulators, for example. What you will also see here is that kind of the typical approach for the robots is so-called the three-layer architecture. So you have low-level functions that is basically connected directly to the hardware, like device drivers. Then you have the middle layer that has certain meta functions, like, for example, how to prepare a map or how to plan a path. And then you have the higher level of the applications that uses these middle layer functions to combine them into a bigger function. So, for example, you want at the higher level, at application level, you may give the order for a robot to go in another room, what in fact is transformed to the fact that you need to have a map of this of the area. You need to plan a path between the two rooms. Then you need to navigate and using probably some dynamics or kinematic properties. So these higher level functions just use this again, these lower level functions as already prepared blocks. Okay. So as we will have a special lecture dedicated especially about ROS, but at the beginning, what we may say about it. So, firstly, what was given by ROS when it was developed is that it gave the standardization of some components and interfaces, especially the basic one. So when you, for example, want to send a command, motion command to a robot, to a mobile robot, the standard ROS message has a format also called twist, and it means that you send the forward velocity in meters per second and rotation velocities in radians per second. And how it is transformed into, for example, encoder frequencies for the wheels to be expected is already done at the low-level driver level. So we have certain standard messages, certain standard for map, for path, and so on. So standard interfaces and also standard component. So if we have, for example, a global planner, it receives a goal in a certain type of the message. It produces the output in form of the certain message that is called path. It receives also the map that is also has the certain format. So when you want to prepare your own global planner, you already have predefined what are the inputs, what are the outputs, how it should work. So that's the kind of the standardization that make it easier to exchange the components between different authors. What else we get? We have the environment that provides the communication layer. This is the communication layer that is called the publisher subscriber. It means that it is open channels for multiple data producers and multiple data consumers. It's not peer-to-peer communication as you have, for example, on internet connections, when you have one unit on one side and one unit on another side. Here you can have a connection multi to multi, and the management of the flow of the messages is done by ROS itself. It also adds some component management. So it can determine if the component is connected, registered in somehow, determine when the component is disabled, when it crashes, when it needs to be respawned. So that is also the role of the ROS. And also it also provides some libraries for devices and for certain functions that are already written and implemented that you can use in your system. Okay, before we get to the main lecture, there are two links that you can go for basics and the basics ideas of ROS. So if someone needs to start with it before the lecture about the ROS comes, you can look into it and get some fundamental ideas of how the things works. In fact, it is quite difficult to start with it now because the amount of information you will find is overwhelming, as there are thousands of pages really that write about something, and it's when you are just the beginning your adventure with ROS, it can be difficult to know where you can start to understand of what's going on. So I think these two links are quite good for the beginner, but also we will tell about it later a bit in the next lectures. Okay, so what I would like to present is how it really got used in the real system that was developed here at the university, and it will be the case of the remedy system, and this remedy system is this abbreviation from remote medical diagnostician. So the idea for the system was that we want to allow a doctor to carry a remote medical examination that was especially ultrasound examination that will be similar to traditional. So the patient and the doctor are dislocated, and we want a robot to work to allow these functionalities of remote examination. How it was done? What can be interesting is that we were using the modified V model of the development of the system. So what is V model? V model is an approach to the project that starts that in fact is two-dimensional. It is a standard for example, in Germany for all the government-led projects. So we start here at the top with the user and user requirements and user needs. And what is specific in this approach is that at each level, together with the requirements, you already prepare the tests. So you already know how you will be testing it. So you start with user requirements and functional design, and at the same time, you design of how the whole system will be evaluated. Then at the second level, you prepare the architecture, and on the second part, you plan how the system will be integrated. Then you divide it to the components. That's what we already said about. At the same level, designing the way of the component evaluation. And finally, we have this low-level component implementation when you prepare the mechanics, electronics, and software, when you make it working. So the process is like that. You start here with the user requirements, split it to a smaller and smaller parts, each time remembering how you will test these parts. When you go to the bottom level, you implement it. So you prepare the working parts of the system, and then you go back making the tests according to the already planned specifications. Okay, the V model, the standard V model is just a one pass. So we just go to the smallest parts, and then we go back to the final system. But of course, as we said, it is a cyclic process. The project had to be limited in time, so we assume that we will have like three rounds of this V system. So firstly, starting with the the results of the first cycle was the virtual prototype. The second was the laboratory prototype, and the last one was the functional prototype, so working in the real environment. So that's how it was done. Okay, so what happened? We of course needed to get the pure idea of the remote examinations, specify somehow. So firstly, what examinations can be done, and how it was defined. That was from we needed to talk with doctors, with patients, with the owners of the owners or managers of the medical units, of what is really needed. So what is needed and what is useful to be done remotely. So the results were a certain group of the examinations that were important, information that we need to have these two physically separated locations, that we need a doctor telepresence. That was something that was mentioned to be very important, that the patient sees a doctor all the time. So he has really not only sees the robot that makes the examination, but can see and hear the doctor that is available, and so on. So the refining of the idea led something to such drawing. Okay, we have one station, we have another station, and that's how it was planned to work. Okay, so how exactly it happened, you may find in how the process was going on. You will find in the paper that was attached to the lectures. So you can see, you can then find how the idea was developed, exactly how the what process was used to discuss the potential users of the system, to determine of what exactly is important. So what interfaces they would like to use, what dimensions we need to have, what should the robot do by itself on that system. So everything was not only the ideas of the developers, but all of the ideas had to be consulted or even verified with some virtual simulation presentations with the final users. Okay, so when the idea was ready, then you needed to divide the system to the components. And as you can see, the system became quite complex. Again, if someone wants to details, I say, okay, you can look into the paper. We have the patient side, we have the diagnostician side, and lots of functions that needed to be implemented for each of the component. The final results that we got was this robot working. So the mobile platform with an arm making the ultrasound. Here you can see the ultrasound head that was making the examinations with telepresence of the doctor, with the full information from the patient side, with the 3D vision. On the other side, where the doctor works, there was the first visualization from different perspectives. There was a haptic interface that, again, someone doing haptic paddle, one of the group doing haptic paddle will know what it is, and the others probably by the end of the semester will also know what do we mean by that. Some additional controls, as there were quite many parts to be controlled. Yes, you needed to control the robot platform, robot arm, and the medical device that is attached. As you can see, many parts that needed to work together, and it's good to have this the idea in the form of some the drawing of the system quite early, to know of what is connected to each part, how these things work together, firstly on the higher level, a little bit later on the lower, when you have exact inputs and outputs defined for each part of the system. And then I think it can be interesting for you to look of what really happens in such a design. So how to combine designing the hardware, designing the software, and testing to make the final system to be working. Okay, the system was working. We had some examinations done between the doctor that was located in Wrocław and the robot and the patient that were located in Lublin. So it was really remote, 200, 300 kilometers away, and it was possible to make this examination. So okay, so what is so what was needed to make this all this process to be successful? So firstly, each of the parts of the process had certain results that we expected and needed to get. So there were user studies. So users needed to define of what they need. As the results, we were getting the functional scheme of the robot. So what are the possible cases of usage of the system? What are general requirements? It was not visible on the drawing, but these were the kinds of the requirements, like, okay, we need to have what should be visible on the screen for the doctor, what should be the velocity of the robot, what should be the minimum or maximum force that are used. All of this was a big table of the parameters that were defined by the partially by the users, partially, but we cannot only rely on users. we also need to define some technical parameters from other sources. So, for example, to know what is the maximum allowed delay between the movement of the robot and the perception of this movement by the haptic device. It is already known from some research, so you need to make a literature review to know that when you want to have a force feedback on the haptic device, the maximum delay cannot exceed 300 milliseconds. So after that, the user will not feel the force natural, and it will more disturb than help to him. Then you have certain legal requirements. Yes, so you not only design the robot in any way you wish, but you need to fulfill certain regulations required by the law. So for the medical devices, you have quite strictly defined norms that you need to follow to be able to use the device later. And also some technical constraints. So, for example, if you want to know what can be the dimensions of the robot, or what must be the capabilities of the mobile robot that is going to be used in a hospital, you also have a certain legal document that says about the constructions of the public buildings, that define of the width of doorways, how steep the ramps can be, how much space must be in the lifts, in the corridors, and so on. So everything of that is the part of the first stage research. Then quickly what we have. This procedure also specified this. We are saying about the V process. So the V0, so the first cycle results were in fact the requirements table for the qualitative and quantitative. So when we can measure, or we cannot measure, but what requirements needs to be fulfilled. Then we're saying about the prototype, and not only preparing the prototype, but also what will be the evaluation procedure, how it will work with the end user, so what they need to test with the prototypes, and how to identify the problems that we have, and then also the plan for the second cycle, what will happen there. So the new update of the requirements, the final project. In fact, maybe you have noticed in the paper that in some tests the robot was not looking that well, because the tests were done on a those were the images from the tests that maybe we can return to it. So when you look at the paper, you will notice that okay, we have different stages in here. So you could see the final robot here, but you can see the images from the intermediate tests that were, for example, when driving on a corridor. Well, you had no covers for the arm, no covers for the platform, and the user interface was not so friendly at the beginning. Then somewhere here you also can see that okay, partially the arm is already finished, but the bottom part is still has some temporary covers. So as you can see, all these prototypes have certain role in developing of the development of the total system, and all this the test do not need the final system to be performed, and you only need this part of the prototype that is in fact needed at the certain stage of the test. Okay, so that should give you the overview of how to deal with the complexity of the design of the. Here we were talking about the robotic project, but in fact any complex hardware-related projects will need to deal with similar problems. What is worth to remember? So these issues of, firstly, it is not a single linear process. You need to be ready and you need to plan time to get to the certain level of the functionalities, test them, and be ready to return few steps back and redesign things that are not working correctly. Secondly, divide the projects to the smaller parts, to the components that are independent, because then it will be easier to develop it more quickly and with a greater rate of the success. Thirdly, work on the tests at the very beginning. So when you start division of the system to the smaller parts, you should already know how you are going to test each of the part, if it really provides the required functionality for the whole system. And an important part that maybe not that important, not so crucial right now for the projects you are doing here for this course, but that will be needed for any project you do in future, is that the projects are not done for themselves. They should incorporate the user and the user needs, user requirements, and the higher activity of the user and test with users you have during the design and implementations of the project, the higher rate of the success you have. Because the worst thing that can happen is that you spend a lot of time on the design, and at the end the user says that it's not what it was expecting, and that the product is not what they need. Okay, so that will be the summary of today. And as I said, probably the next lecture will be about the ROS basics, because I think it's good to start with it soon, as some of the projects depend on the informations from depend on ROS. So it's good to have this knowledge in early. Okay, so we'll finish for today. If you have any questions, please ask. Okay, so if there are no questions, so thank you for your attention. And with some of you, we meet today during the projects in the afternoon.